Okay, so then just start now with what we are going to do in the rest of the lecture, which is consider effective theories in collective phenomena. So I should have probably told like that this collective excitation of the weakly electron gas, here's the plasmon. It's called plasmon mode. Okay, so it's a collective excitation of the electron gas. So now this brings us then to the effective theories. And collective phenomena. So let's just make some conceptual considerations and just, restate some of the things that I already said so far, and then try to. So let's first see, what we did, reflect what we did so far, then see that there can be some problems appearing there in the way we treated right now the problem, then see what would be a better way how to do the things, and then what we will formulate is a program how one can then, so the better way how to do it is then the idea of looking at effective theories, and we will formulate some program how to construct these effective theories. It's like a 5-step program, so probably we'll end then here today, and then we will just follow this program to construct effective theory for the example of the weakly interacting electron gas, and hopefully also for some system where you have magnetism going on. And if there's a continuation, then we will see how this also appears like. So this then is the thing, like you can study superconductivity, effective theories for this system and so on. So this, if we are going to continue next semester, then this will all be discussed. But let's first reflect what we did so far and then formulate some general problems. So, okay. So as I already said, so far what we did is we formulated perturbation theory around the non-interacting reference state. And this is something we didn't think too much about, we just did it. We said, well, we guessed, well, if we have weak interactions, well, that can change some things, but it should be fine to just say the weakly interacting theory isn't too different from the non-interacting. But this was just a guess. We never really reflected on this. But what actually can happen is that this is not the right thing, because arbitrary weak interactions can sometimes just change the ground state of the system, and then what you're trying to do is, in a way, you're trying to develop a system or like a theory around the wrong reference state. And this, of course, should lead to problems, and technically this means that what one encounters in this kind of approach where you just chose the wrong reference state is that there are instabilities appearing. Okay, just telling you, well, if you have weak interactions, to change your ground state. So the non-interacting reference state is not the right thing anymore. It's unstable. There's instabilities here. Okay, so let's state this. So the perturbation theory. Around the wrong or the wrong reference state instabilities. There will be some divergences popping up, and we will see examples of that. Actually, we saw one example which was just a Plasmon frequency where you have collective oscillation. So this means that, well, if we cannot always rely on making perturbation theory around the non-detecting state as a reference state, we need some systematic way then how to avoid these kind of problems that can appear, that we didn't encounter but can appear. So what we need to have is we need to develop a theoretical frameworks that achieve the following. So first, it should be capable to detect and write reference states. And the way how it will detect, like the way we'll see how one can do this is that the right reference states will appear as mean fields of this effective theory, okay? So let's call them these right reference states the mean fields of the system. Just, I mean, think again of the weakly interacting electron gas, where now you have like put in some weak attractive interactions. Well, there should be not the reference state, the non-interacting system, but the right reference state is that where you have the Cooper pairs, like paired electrons that form the Cooper pairs of the system, which then appear here as the mean field of the theory. Okay. Then once we have found one has found an effective way how to detect the right reference state, we will also want to consider again the effect of interactions on top of this reference state. Okay, now this will be interaction between the effective degrees of freedom, so we want to effectively then apply perturbation theory now around the rightly chosen reference state. So in the case of the weakly interacting electron gas, we didn't think about the problem, but also no problem appeared because, like in what we considered, the non-interacting reference state was the right reference state, and then we could like look at perturbatively what is going on around this reference state. Now, here in the more general context, you first want to detect the right reference state, and then have some effective way how to apply perturbation theory or perturbative methods around these now reference states, around these states. Now, here what I mean by effectively is that what we saw already in this example here, that I mean we started out doing our diagrammatic perturbation theory by drawing electron lines and like the interaction propagator lines, the wiggly lines. But then in the end what we saw when we looked at made an analysis of these diagrams, we saw that the electron propagators in this problem always appeared in some specific form. So there were elementary building blocks that all diagrams were made up from, which in this case were just the bubbles. Okay? So there should be then some effective way how to do perturbation theory where one doesn't think so much anymore about the microscopic ingredients like drawing the microscopic electron lines, but where one already takes like the more, not microscopic, okay, so here like we made formulated in a way using the microscopic degrees of freedom, but then we found there is effective building blocks which are taking care of all the physics, which here were the polarization bubbles, and this were not single electrons anymore, but they were bosonic degrees of freedom. It's a part of the whole excitations. So instead of thinking about the microscopic degrees of freedom, there should be some way how to identify the physical relevant building blocks and then formulate perturbation theory not anymore as microscopic, but in this physical building blocks. Okay. So this would be the third thing that ideally we know how to do. So we want to do this. Second point of the perturbation theory, we want to do this in the language which draws upon the physical relevant in this context rather than the plain microscopic degrees of freedom. We want to think of these physical degrees of freedom as the fundamental units of the theory. Okay, so as in the case before, we don't have to care so much about single electrons and single holes, but we should just care about like the polarization that is going on due to the creation of an electron hole excitation. So in many cases, this just means that changing the microscopic, let's say, electron propagators, fermionic propagators for composite objects, which then are typically bosons. Okay, these two electrons form bosons. Like in the superconductor, this will be the Cooper pairs. We don't have to think so much about like the single electrons anymore because they will just pair up as partners to form pairs. Okay. And actually now, up to now, what we did, everything like the perturbation theory and so on can all be done also using just normal operators, so the operator formalism. So in the end, what we did only was using big theory here in kind of diagrammatic language, but we could have done all this just using operator formalism. But now when it really comes to these effective theories, we will see the power of the function integral methods, because they are much more flexible. So what we are dealing with always, we start out from microscopic theory in terms of some functional integrals. So the degrees of freedom are some kind of integrals. So we can make change of variables quite easy by just changing the kind of integral integration variables. Okay, this can be used to introduce new degrees of freedom, and then you can always, like, you write down the partition function, whatever it is, functional integral as an exponential of some action, and we always have methods like the stationary phase analysis, which will allow us to identify certain field configurations which play a relevant role. So if there is stationary phase, the stationary phase analysis, for example, shows you that there are solutions, non-trivial solutions, well, these then correspond to reference states which are non-trivial or which correspond to the mean fields which differ from the reference state of the non-integral problem. Okay? So let's then see. Okay. So let's, in the remaining 10 minutes or whatever, 5 minutes, just then formulate a program which is like a 5-step program, which is using the power of the functional integral method to employ like 5 steps by which we can construct a theory which achieves these things that we actually want to. Okay, so let me just write down the 5 steps that we are going to follow, and these are then the steps that we are going to first apply for the weakly attacking electron gas inequality. Okay? So this is then the functional integral or the functional approach . So there's one thing that I should still mention is that, well, typically if we want to find the right reference state, or we mentioned, so typically one does this by some stationary phase analysis. So there should be always some, let's say, large parameter which will allow us to do a stationary phase analysis, or like there should be some parameter, that large parameter that allows us to develop this theory. So in the weakly interacting electron gas, we also used heavily that we're interested, or that we were focusing on the large density limit, which corresponds to the weak interaction limit, to like identify a certain subclass of diagrams. So let's assume that we have a problem where we have some large parameter, okay? So if we don't have any such large parameter, then, I mean, typically in bad shape, but just here and see. This means, so just think of the example that we had where we used this parameter Rs, which was proportional to the Lewis density. So let's formulate a program which consists of 5 points, and which is the following. So the first step, what we do is we identify the relevant structural units of the theory, which is typically done by diagrammatic perturbation theory here around the non-interacting reference state, I call it diagrammatic perturbation. Okay, so what I mean here is, well, if you're confronted with some kind of problem where you don't know what is going on, always take, like in the weakly interacting electron gas on other problems, just start out doing some perturbation theory around whatever you know, like the non-interacting problem, which we know, like I said, can be that's a wrong ground state, but just do this and try to identify, using the large parameter, the right kind of diagrams which should be the most relevant. Yeah? So that's actually what we did also in the weakly interacting case. We looked at the first order contribution to the free energy and saw that, or in the second order we saw that there's a certain class of diagrams which are more relevant than others. Okay, so if you have a large parameter, the problem, typically you can identify a certain class of diagrams which are relevant in some sense. Now, in the weakly interacting electron gas, this was just by saying, well, these class of diagrams are much larger because of this phase space argument than these kind of. In other problems, you can see actually the instabilities popping up here. So you see, well, there are certain diagrams, but if you sum them, you see, oh, there's some divergences happening, some instability, which tells you then, well, the reference state, the non-interacting was wrong, but you already identified the right, let's say, structural units when you did the diagrammatic analysis. Now, this is still very abstract, but we can exemplify this in more examples, or also see that there's actually always like 3 kind of interaction channels which can be relevant, or maybe a mixture of them, but just as here an example, so what we mean here, for example, the weakly interacting electron gas was this particle hole bubbles. Okay? So this is the first step that you do. And then in the second step, now this is the new thing, where the function integral method becomes very powerful, is that you introduce a new field. Say you start out from some theory of electrons, so you introduce some new field, which I call phi, that now encapsulates the relevant degrees of freedom of the low energy theory. And again, this will become more clear once we go really through the steps more carefully. But the idea you can think of right now is, well, as said in the weakly interacting electron gas, the single electron lines didn't play such a big role, but we saw that their combination of a particle and a hole, product of two Green's functions, were what appeared. Well, and we could then introduce some, just in this case, bosonic field that corresponds to this collective or this combined propagation of the particle and the hole. Okay, so this would be here. Well, we will explicitly see that this is related then to the density. Okay, the creation of an electron in the hole, and in this case, the relevant degree of freedom is just density fluctuations in the weakly interacting electron gas. So once one has introduced this degree of freedom, what one is encountered with. So here one is encountered like we're focusing right now on Fermi theory. So here we start out from some theory of electrons, which could be interacting, or later on like in disordered environments and whatever. And one identifies some composite object, some typically bosonic field, which is relevant. So one introduces this new field, and then what one wants to do is one wants to end up with a theory just in this composite object. So what one wants to do is one wants to trade the integration over the microscopic fields, which here would be the electron fields, for an integration over this new degree of freedom. Over 5. Okay, so you start out from representing from partition function, or later on like correlation like the generating function for correlation function. You represent in terms of a functional integral over your microscopic fields. But once you have found like what are the real physical fields, you do not want to think about electrons or whatever anymore. So you want to trade the integration over the microscopic for the integration over the effective fields, meaning that you then represent your partition function or your generating function just in terms of these effective fields. So this step is also known as the Hubbard-Stratonowicz transformation. And this just builds on a very simple integral identity it's just a very simple integral identity that you use here, and changing this degrees of freedom actually is an exact step. So up to there, you didn't do any approximation or whatever, you just make in a way change of variables when expressing your generating function or partition function. So then comes an important step, which is that you expose, then once you have traded your microscopic degree of freedom for this effective, you can again represent, let's say, your partition function or generating function as a functional integral where you weight every field configuration by some action. Okay, so you have an effective action for this degree of freedom, and you can expose this then to stationary phase analysis. So the low energy content explored by subjecting the resulting action S of phi to stationary phase analysis or saddle point analysis. Oh, saddle point. And this is typically justified by the large Fermi that you want to have in the series. Okay? And then at this point you will also see the instabilities that we mentioned popping up, namely if we have non-trivial solutions to the saddle point equation. Okay? So at this stage, instabilities may show up, and they always are an indicator, an indication that you're dealing with some physically interesting problem. Physically interesting problem. Okay, and then the last step, what you then want to do, well, you have identified some mean field configuration, but then of course you also have to consider fluctuations around the mean field. Okay? And this means that you can develop then some theory. You can write the action as the mean field contribution plus fluctuations around it, and then write down effective theory for fluctuations. Fifth step, nature. Collective excitations what's the ground state, can be explored functional integral around the mean field which is here equivalent to I mean, the solution of the saddle point equation, so the saddle point I could also say. Solution to stationary phase analysis or solution of the saddle point analysis or mean field equation. Okay. So this means solution of saddle point equation. And then from the low energy effective theory that one has when one expands around this reference point, one can then calculate whatever observables, for example, one is interested in. From low energy action, one can calculate physical observables. That's the final step. Okay, so this should just give you an idea, and we will fill this all with more life by once going through the example of the weakly interacting electron gas. So this we will do like next lecture, going through the 5 steps, and then hopefully, yeah, I think we will have time to discuss a second example.